In Module 1, we're going to see what are the key probability distribution that are required to perform reliability analysis. So why? We need probability distribution in order to describe what is the possible occurrences of diverse physical phenomena. So the one that we're going to see in the context of this reliability course are the normal distribution, log normal, gamma, Gumbel, and beta. So we're going to start with the normal or Gaussian. We're going to see its extension to the standard normal space. We're going to look at the log normal, gamma, Gumbel, and beta. And that places us here in module 1, where we're still in the core theory of probability. So first section, we're going to cover the normal or Gaussian distribution. We're going to look at the univariate case, multivariate case. What are the special properties that are extremely powerful for the Gaussian or normal distribution? So from now on, whether I use normal or Gaussian, assume these are two synonymous. Then we're going to look at an example of application of conditional distribution in the Gaussian case. And then we're going to look at what happened when we add Gaussian random variables. And finally, we're going to see how can we apply, how can we use it using Python. So first, the Gaussian or normal distribution, we're going to say that x, a random variable because it's capital, is distributed like a normal distribution with parameter mu and sigma, okay, just as we saw before. And we look at it very quickly before, but this is the analytical expression for the Gaussian probability density function PDF. And the property of the Gaussian PDF is that it's defined over the real space. So minus infinity to plus infinity. So if I evaluate that PDF at a value lowercase x, it's going to return me the height of the PDF at that specific location. So the main parameter of the Gaussian distribution are its mean mu and standard deviation sigma. Where here, if we look at an example for that Gaussian PDF with mean 1 and standard deviation 1, you see that the crest or the top of my curve is centered at the mean, and the width of my curve is controlled by the standard deviation. So in order to interpret those parameters, you could see that the mean represent the center of gravity of my probability density function. If I would want to balance that PDF on my finger, it would have to be placed exactly at the mean. If I want to look at the standard deviation or variance, so variance is the standard deviation square, that would represent, to make an analogy with a structural cross section, it would be the inertia of my cross section, measuring how much my material is spread around my center of gravity. So the variance measure how much my probability density function is spread around its mean. And then if we want to look at the CDF, so CDF is going to be the integral of my PDF with respect to the x from minus infinity up to x. So in this case, if I want to evaluate up to 0, that's going to give me that area under the curve. So if I want to evaluate that CDF at 0, it's the integral of that PDF from minus infinity up to 0. And if we look at it on the CDF, if we just read the CDF at the value of 0, we're going to get its value. In this case, it's 0.16. So 0.16 corresponds to that shaded area in blue here. So if we look here, how would it look like if we start playing around with it? Give me a sec. So you see, so we have the PDF here, we have the CDF, we have the mean here in blue, we have plus and minus 1 standard deviation with these being bound. And we see that if I play with my first sliders, which gonna change the mean value, we're gonna see that we're gonna have a translation. So we're gonna have a translation both of the PDF and CDF without changing the shape of itself. Then if I play with my second slider, which will control the standard deviation, we're going to see that we're going to get some narrower curve, which is going to make it my CF look much steeper until it looks almost like a step function. On the opposite, if I make it really bigger, I'm going to make my slope more progressive. And keep in mind that here the PDF always seems to be the same height. It's because I'm adjusting here the vertical axis automatically. But at the end, it must always satisfy the criteria that the integral underneath the curve equal 1. So if I make this integration very small, you're going to see that I might get some PDF value that are way above 1 because I must maintain the integral under the curve that makes a unit. Okay, that was a univariate case. Let's look now at the bivariate case. So if we extend the formulation in the two-dimensional case, it would look like this, where now we have 5 parameters, the mean for each of my variable, the standard deviation for them, and my rho correlation coefficient that express the amount of linear dependency I have between my two variables. So if we look at the joint PDF, either with respect to a surface or a contour, it would look like this. So both are the same PDF, just with a contour or a surface. And you can see the marginal PDF represented here for x1, the marginal for x2. And here, the kind of squashing we can see between the PDF of x1 and x2 is caused by my 0.6 correlation coefficient. So if we look more closely at how does it look like? So just going to increase the size a bit here. So you can see this is the same example. I have 5 sliders for my 5 parameters. So if I change the mean for x1, I should get a translation along my x1 axis. So you can see that x2 is remain unchanged and the shape remain unchanged by shifting the mean. Same thing if I move x2, I'm going to have a translation against my or along my second dimension. I move sigma 1, I'm going to only change the spread around my first direction. And you can see how now my marginal PDF gets updated as I change these values. If I change my second one, this is the spread that changed along the second direction. And finally, if I change rho, my correlation coefficient, what's going to happen is I'm going to here change the elongation. So if I have now a negative correlation, something close to -1, what we're going to see is that we model something for which if we have a high value for x1 as a realization, it increases the likelihood that I'm going to have a high negative realization for x2. To the opposite, if I put a high positive correlation, I'm going to say if I have a high realization for x1, I'm likely to have a high possible realization for x2. Okay, so this is what happened. And if I go up to the extreme case where I put something that's very, very close to 1, you see that the PDF almost collapses on itself. So this is the influence of the 5 key parameters. And when you look at the multivariate normal PDF in larger than 2 dimension, the effect of the parameter is very similar to what we see here for 2 dimension, but expanded for the multivariate case. So this was for the multivariate PDF. We can look now at the multivariate CDF, cumulative density function. So here, if we want to obtain it, we need to integrate with respect to each dimension x1, x2, the joint PDF with respect to my two variables. So it's going to look like this. So what you're going to see here in that red curve is the marginal CDF for x1, marginal CDF for x2, and we have the contour corresponding to that surface here. So if we look at this in here, you're going to see we have the same thing here. So we shift the mean. You're going to see that translation of the kind of the wall or the ridge of my CDF with respect to the axis moving around. So same thing for my axis x2. If I move my slider x1, you can see that we change the spread along one direction. We change the spread along the other direction. And if I play with my correlation coefficient, what you're going to see is that I'm going to change the sharpness of my ridge here, representing the interaction between x1 and x2. If I make it lower, it's going to get smoother. If I make it higher, it's going to get much sharper until having a completely square edge. So this is the influence of all my 5 parameter on the Gaussian CDF, multivariate Gaussian CDF. So if we want to generalize that formulation for an arbitrary number of dimensions, we're going to say that x is distributed like a multivariate normal, multivariate Gaussian parameterized by a mean vector and a covariance matrix. So if I have an n-dimensional random vector that is Gaussian, where mx is going to be my n-dimensional mean vector, and sigma x my n by n dimensional covariance matrix, that looks like this one. Then this would be the general form of the multivariate Gaussian distribution. So now we have here a kind of quadratic form that is weighted down by my covariance matrix. We have my mean vector, and here as a normalization constant, we have 1 over 2 pi divided by n, my number of dimension, the determinant of my covariance matrix. Remember, the determinant measure how much we expand or squeeze the space with the linear transformation. So that is adapting the normalization constant to make sure that the integral is 1 by the how much my covariance matrix transform my space. And we can use this from the one-dimensional case up to an arbitrary number of dimensions. So remember, if we want to represent our covariance matrix, we can factor it into a standard deviation matrix where we're going to have the standard deviation on the main diagonal, 0 elsewhere. We can have my correlation matrix, 1 on the main diagonal, my correlation coefficient for every pair of variables on my off diagonal. And remember, these matrices are symmetric. So if I want to obtain my covariance matrix, I can obtain by d r d. Okay, so we're going to look now at the key properties of the Gaussian random variables that are very useful for reliability. So the first one is that they're going to be completely defined by their mean vector and covariance matrices. So once I know them, these two, I know everything there is to know about my Gaussian random variable. We can have marginal distribution that are normal. So what does it mean? It means that once I have my mean and covariance, I can directly obtain the marginal distribution without the need to integrate how we saw in the module 0, okay? We don't need to integrate explicitly because here the marginal distribution are directly represented by the components that are already available in the mean vector and covariance matrix. I can directly extract the mean value, the expected value or mean value, and standard deviation from these two. And that's going to directly give me the parameter for my marginal distribution. So I have access to my marginal without needing to integrate. And this is really powerful. We're going to use this property later on. So when we don't have any correlation in a Gaussian case, that implies that my random variable are statistically independent. This is not true for all distribution. It is for the Gaussian. We have a special property with the central limit theorem that says that the asymptotic distribution originating from the sum of an infinitely many number of IID, so independent identically distributed distribution is normal. So what it means, okay, I'm gonna simplify this. So if we sum infinitely many random variables that are all distributed in the same way, but could have an arbitrary shape, the result from the sum always tend to a Gaussian. So for instance, if I have n variable that for n that tends to infinity, if I sum these random variable that could be arbitrarily distributed, doesn't have to be normal, could be anything. The sum of these variable will tend to a Gaussian distribution, okay? And this strictly hold only for n that tends to infinity, but in practice, this is very useful because for it to be practically indistinguishable from a Gaussian, it doesn't take very large n. Already with n equal 5 or n equal 10, it's super close to a Gaussian, no matter what is the distribution you're starting from. So that makes it very easy, and that's why we see the Gaussian so often in the phenomena we're trying to model, because when we have a lot of factors that are compounded or added together as sources of uncertainty, the resulting variability that we observe is looking very closely to the Gaussian. Other property, the linear function of Gaussian random variables are still Gaussian. This is what we saw also in the previous module. When we add linear function of Gaussian, we saw that we can have exact analytical expression to compute the output moment of those function, and the distribution is still Gaussian. So we saw that if we have a function y equal ax plus b, where a is a deterministic matrix, b is a deterministic vector, we have the exact moment for the output where the expected value is going to be a mx plus b, and the covariance is going to be a sigma x a transpose. With the Gaussian, the conditional distributions are normal, okay? And this is very useful to use observation to gain knowledge about other variables, okay? I'm going to detail this. So imagine that you have a big vector of a random variable x that I can partition into two subsets, x1 and x2. So I can also partition my mean vector by m1 and m2, and my covariance matrix. Sigma 1 is the covariance associated with x1, sigma 2, 2 covariance associated with x2, and sigma 1, 2 or 2, 1, these are just simply transpose of each other, where sigma 1, 2 is a cross covariance between the variable in x1 and the variable in x2. And I can obtain this by just really partitioning my covariance matrix according to the split I'm deciding here. And what we can do with the Gaussian conditional is that we can directly have access to a closed form solution for conditioning, okay, for the conditional distribution. What did it mean? If I'm observing the set x2, I can directly have access of how observing x2 changes my knowledge of my first set x1. And remember, we obtain such a conditional by dividing the joint distribution for x1 and x2 by the marginal for x2. And this division here has a closed form solution in the case of Gaussian. And the result is that it's still Gaussian, where the conditional mean vector and covariance are obtained using these two equations. So if we look at them in terms of one or 2D case for a single x1 and a single x2, it looks like this. So my conditional mean for x1, given that I have observed x2, is the prior mean for x1 plus correlation coefficient times sigma 1 plus x2, the observed value for my second variable, minus its mean divided by standard deviation. And for my conditional standard deviation for x1, knowing that I've observed x2, it's sigma 1 times square root of 1 minus rho. And note that the conditional mean depends on the actual value we observe. The conditional standard deviation is independent of it. And these are for the kind of univariate case. This is the general case for an arbitrary number of dimensions. So if we look at an application of these Gaussian conditional, so imagine that we have two of the beams that could be on a span of your common like bridge you can see almost everywhere. So we're going to say that we want to model the strength, the resistance of these two beams. So our prior knowledge of these two beams, since they were built in the same factory by the same worker, using the same material, using the same like construction drawings, we can assume that our prior knowledge for x1 and x2 is that the prior mean is 500 kilonewton meter, the prior standard deviation is 150. We have the same thing for the two beams, and given that they were built in very similar conditions, we can assume that if we have a higher than expected resistance for x1, we should have the same higher expected resistance for x2, but this is not exactly right. So in this case, we assume that the correlation coefficient between these two beams is 0.8. So right now, we're going to assume that 0.8 is given. Later on, in the later module, we're going to see how can we estimate such a parameter from the data. But for now, let's assume 0.8 is given. So the question is, if I go in the lab, I test one of these beams, and I observe that the beam 2 has a strength or resistance of 700 kilonewton meter. How does it change my knowledge for x1, observing that x2 has a resistance of 700? So to answer this question, we can use the Gaussian conditional. Okay, we're going to compute our conditional mean, conditional variance, and the result is going to be 660 and 90. So my prior was 500. After observing 700 for beam 2, the expected value jumped to 660, and my variance was initially, or my standard deviation was initially 150 kilonewton meters. It drops down to 90. So how do we obtain this? We use the Gaussian conditional, we express the joint. So we say that the mean vector for my two beams is 500, 500. The covariance matrix is 150 square on the main diagonal, and my covariance term is 0.8 times 150 times 150, and this matrix is symmetric. To obtain my conditional, I would divide my joint by the marginal, and this directly gives us the expression for the conditional. I can use these two expressions if I plug in a number where my observation is 700 for x2. The result would be 660, and for my standard deviation, it would be 90. So if we look graphically at what happened here, so we can see my joint and my conditional. So we're going to look directly at the 2D distribution. So on the left, what I have is the joint PDF for x1 and x2. So this is the joint PDF. We have the marginal here for x1, the marginal here for x2. And what we have here in pink is the slice for x2 equals 700. Because my observation tells me that not all these possible values of x2 exist. The actual one is only this one as 700. So if I want to represent my updated knowledge is represented only by this slice in my joint. But the problem is that that 2D surface normalized to 1. What does it mean? If I integrate the area under all this curve, the volume under this surface, the volume equals 1. But when I take just a slice into that distribution, that pink slice, the integral under, so the surface under that pink slice doesn't integrate to 1. If I wanted to make it integrate to 1, I need to divide that joint PDF evaluated at 700 by the height of my marginal PDF for x2 evaluated at 700. And this is what we do when we evaluate the Gaussian conditional. So this is the result of that Gaussian conditional f of x1 given x2. So in that case, we can see that when we're at x equals 700, this represents the marginal PDF for my resulting knowledge of x1, given that I've observed x2 equal 700. Okay, and you can see that it looks like a ridge like this, because if I change the value of x2 I'm observing, it's going to change my expected value, posterior expected value of x1. However, it's never going to change the standard deviation. So this is all consistent with what we saw in our equation, where sigma is independent of the actual value we observe, but the expected value is dependent upon it. Okay, so if we carry on with the properties, we're going to look a little deeper at the addition of Gaussian random variable. So let's assume we have two variable, x defined by mu x sigma x, y defined by mu y sigma y. So if we assume that both x and y are statistically independent, and I want to compute the sum for z equals x plus y. So we saw from the previous expression of linear function of Gaussian random variable that the output is still going to be Gaussian, where in this case, I'm simply going to add the expected value to obtain mu z. I'm simply going to add the variance for obtaining sigma z. This is in the case where they are independent. But if the correlation coefficient is not 0, so they're not independent, in that case, the formula would become mu x plus mu y, the same thing for the mean, but the variance now is going to be represented by sigma x plus sigma y, plus we need to take into account the covariance term. So 2 times rho xy times sigma x times sigma y. So this is going to be my variance term that's going to take into account the possible dependency. And if we want to generalize this for the sum of an arbitrary number of Gaussian random variables, it's going to be simply, we're going to sum the terms of the expected value, and we're going to need to sum all the terms that we can have in the covariance matrix from the vector we want to sum on. Okay? So in this case, cov of x, y, xj is the ith and jth terms of my covariance matrix. So let's look at an apply example of this case. So imagine we have a cable like this one, which is made of 50 steel wires. Okay, we're going to assume that each of the wires is made of steel that has a ductile failure mode. Okay, so if we reach its limit state, it's going to increase in length without additional increase in force. And then we have the knowledge that each of these wires as a prior resistance of 10 kilonewton with a standard deviation of 3. And the question we want to answer is, what is going to be the resistance of that cable if our knowledge of the resistance of each wire is this one? So we can obtain the distribution for the resistance of the cable as the sum of the resistance of each wire, okay, for my 50, the sum over my 50 wire. So if we use the hypothesis that each of the wire, their resistance is independent from each other, we're going to model the strength for the cable as a Gaussian, where the expected value is going to be 50 wires times 10 kilonewton, and the variance or standard deviation. So the variance is going to be 50 times the variance of each cable. So if we take the square root to obtain the resulting standard deviation, that's going to give me 21. Okay, so that's would be the variance for my cable if the resistance of each wire is independent. If we go at the other end of the spectrum, we assume that the resistance of each wire is fully dependent. So my correlation coefficient would be 1. In that case, I would obtain the resistance or the parameter for my distribution for the resistance of the cable. For the mean, it's still the same thing, but the variance now, it's 50 square times my variance for each wire. Would give me a standard deviation of 150. So keep in mind, we said earlier that if we want to model the sum of such sum, for the variance here, we need to sum all the term in the covariance matrix. So the covariance matrix, if we are independent, has only non-zero term on the main diagonal. So I'm going to have in a 50 by 50 covariance matrix, 50 terms on the off-diagonal term. So that makes 50 times 3 squared. If I have a fully dependent correlation matrix, any term in my covariance matrix are going to be equal to 3 squared. So I have 50 square terms that are equal to 3 squared. That makes 150. So if we look at this graphically, what we see is that if I make the assumption that my resistance is independent from wire to wire, we see that adding more wire will globally reduce the spread of the strength of my cable. On the opposite, if my correlation is 1, all the strength of each wire is independent from each other, I'm going to have the same spread in my cable that I have in each of my individual wires. Okay, so in this case, having independence will reduce my spread because some of the wire are going to be higher than average, some are going to be lower, which an average is going to shrink the global variance. Okay, so if you want to use the Gaussian or normal PDF or random variable using Python, you would need the sciped package if you want to plot matplotlib and numpy. So we're going to define the mean value and the standard deviation. Then we want to plot the PDF for a Gaussian. So what we're going to do, we're going to define what value x we want to plot on. So a range -3 to 3 by increment of 0.01. Then we can access we can evaluate the normal PDF, so norm.pdf, the values on which we want to evaluate it, and my 2 parameters. We can do the same thing for the CDF, and we can plot plt.plot the value on which I want to plot and the value of my CDF. I show my plot. So this is for a simple 1D case. If I want to do a multivariate case, I'm going to need to define in the bivariate case my mean values, my standard deviation, my correlation coefficient. I need to define a tuple on which I want to plot. Since I have a 2-dimensional case, it's going to be a two-dimensional vector. So this is x1, this is x2. So I define my mean vector, I define my covariance matrix on a 2x2 matrix. And now I can evaluate my either joint PDF or CDF, multivariate normal.pdf or .cdf, where the tuple I want to evaluate it with my mean vector and my covariance matrix. Now, if I want to expand this and I want to plot an entire joint PDF, it looks like this. So I'm going to define my parameters. So the same as before, going to define my mean vector covariance matrix. But now I need to define a grid on which I want to plot either my 2D surface or my contour. So I'm going to need to define how many division do I want for my grid, the min and max span. I'm going to define a first vector for the axis x1, going from min x, max x, and the number of division I want to do. Then I need to make a grid on which I want to evaluate either my joint PDF or CDF. So I'm going to do this using mesh grid for my two vector x1, x2. These are going to give me two matrices that are matching grid for my two coordinates. Then to evaluate it, I need to reshape these two grid into two vectors. So I'm going to use the reshape command. And if I have ndiv dimension along each direction, the size of the vector is going to be ndiv squared by 1. Then I'm going to concatenate these two vectors, each for x1, for x2, to evaluate each of my coordinate by stacking them together. Then I can evaluate that n squared by two-dimensional vector in my multivariate normal. Okay, this is what I'm evaluating here. But then to plot, I need to reshape the output joint PDF, which is going to be a n squared by 1 result. I need to reshape it here to have the shape ndiv by ndiv. And don't forget to transpose, otherwise you're going to get your two-dimension x1 and x2 that are flipped. And then I create a figure. I'm going to add a subplot. I'm going to plot first the surface. So for x1m and x2m, the two here coordinate grid on which I want to plot. And my third dimension is going to be my x1, x2. Then we're going to set the labels. I can add a second subplot for then plotting the contour. Okay, these two use the same input. It's only one is going to be the contour. The other one is going to be the surface. And then I can set the limit, add axis labels. So this is how we can plot using the multivariate normal. Next distribution we're going to see is the standard normal. Okay, this is very closely related to the property of the normal, and this is key for developing the theory of reliability. So we're going to look at the univariate case, multivariate independent case, and multivariate correlated case. And what is going to be very important is how can we perform a transformation between U, what we're going to call the standard normal space, to the general original space. So we're going to say that U, this is a variable we're typically going to use for a standard normal random variable, is distributed like a normal with mean 0 and 1. So a standard normal random variable is simply a normal with mean 0 and standard deviation or variance equals to 1. And typically we're going to represent that standard normal PDF by lowercase phi. So lowercase phi of U is represented by this Gaussian PDF, where we're going to replace the mean by 0, standard deviation by 1. That's going to simplify here that PDF to this expression. And then we can represent the standard normal CDF by simply the integral of what we have here. So this is equivalent to just using the standard formulation for a normal, but evaluating for mean 0, standard deviation 1. And we have the property, we can go from any generic Gaussian random variable to its standard normal space. We can do that transformation by simply taking the generic or arbitrary variable x, subtracting its mean, dividing by the standard deviation. And that's going to bring us into the what we call standard normal space. So let's take, for example, we have this variable x, which has a mean 1, standard deviation 1. We can see that, as we did earlier, if we evaluate the CDF of this random variable at 0, we're going to get 0.16. That represents the area outlined in blue here. So the integral from minus infinity up to 0. If we want to transform this arbitrary random variable into the standard normal space, I'm going to subtract the mean, divide by the standard deviation. So in that case, if I do this, I'm going to get evaluate for mean equal, I'm going to evaluate U at 0, minus 1 divided by 1. So it means I'm going to evaluate at minus 1. So if I evaluate my standard normal space at minus 1, we're going to see that we're going to get exactly the same result for the CDF. Okay, so we can always go back to the standard normal space and evaluate there in the standard normal space. And actually, in the code, for instance, in Python, this is what is done. What is implemented in the code is just a standard normal space, and you're always transforming when you're evaluating an arbitrary PDF, you're transforming the value into the standard normal space where it is evaluated. Okay, so some properties of the standard normal space. So if we assume that all the variable in the standard normal space are independent, so the covariance is equal to the identity matrix, we're going to represent by phi with index or subscript n to represent the n-dimensional standard normal space evaluated at u, which is now a vector, with covariance identity. Typically, we're going to omit, when it's case that it's independent, we're going to omit that identity matrix, just represent it here, and we can obtain that joint PDF by simply taking the product of the marginal PDF because of the independence assumption. So this reduced to this analytical expression where n is the number of dimension, and that double bar represents the norm of the Euclidean distance, so the square root of the sum of the square of all my coordinate ui squared. And the property of that multivariate independent standard normal space is that all the contour of my joint PDF are in two-dimensional circular, but in three dimensions, they're going to be spherical. And in higher dimension, they're going to be hyperspherical, and they're all going to be centered at the origin. So that means that if I can take slice in any directions, they're all going to look Gaussian. And the probability in all direction that are radially going away from the center will have an exponential decrease in the probability density value with increment of the norm of u. Okay, so the farther away I'm going from the original, I'm having an exponential decay. So if we want to look now at a special case where we're going to have the standard normal space, but not independent anymore, the correlated one. So we're going to explicitly represent here that R, which is going to be not the covariance matrix, or at least covariance matrix equals the correlation matrix in that special case. So that's going to be the analytical formulation we're going to have, where U is the value at which I want to evaluate my joint PDF in the standard normal space, and R is the standard correlation matrix we saw earlier, one on the main diagonal. We're going to have our correlation coefficient on the off-diagonal terms. And we can see here what happened if we cut some slices in my joint PDF. These also look like bell curves. Okay, so now we're going to look at the general transformation from an original space X that is Gaussian to the standard normal space U that is mean zero, variance one. So in that case, we can obtain that transformation that we said earlier, U equal X minus mu X divided by sigma X. This is obtained actually by the equality of the CDF. So the CDF evaluated at X must be equal to the CDF evaluated at U. And if we do the expression and we develop these terms, we're going to find exactly these expressions. So this is in the univariate case, but we can generalize for bivariate or multivariate cases. So in the multivariate cases, we have this general case where R could be the non-independent case. We're going to say that going from X, the original space, we can go to the standard normal correlated space by doing the inverse of L, where L here is the Cholesky distribution of R. Cholesky distribution of a square matrix is going to be a factorization, such as we can decompose R into L times L transpose. Okay, so if you do Cholesky decomposition of R, that's going to give you that triangular decomposition. So if you do U equals the inverse of that Cholesky decomposition times the inverse of my standard deviation matrix times x minus mx. So that's going to allow us to go in an arbitrary correlated Gaussian random variable into its standard normal space. And if we look at this visually, you can see that here what we have is we have the original variable with mean 3, standard deviation 0.5. This is the PDF here. We have here the standard normal space. So to go from one to the other, what we do is that we say we must have equality in the CDF. Okay, what does it mean? So it means that if I evaluate the standard space at x equals 3, I'm going to read the CDF 0.77. I'm going to read the CDF of the standard normal space. So it means that the 3 correspond to here 0.74 in the standard normal space. Okay, and we can see this also in that kind of joint graph. So we have here the values for u, we have here the value for x. And if we say that the two CDF must always be equal, so what it means is that for x equals, say, 3.4, here my value of the CDF is 0.77. If I read that 0.77 value here in phi, we're gonna can read the value of 0.74 for u. And here, if we could scan any possible value for x, we would get any resulting value of u that goes along this linear line. So what this black line mean is that we have a linear transformation between the arbitrary Gaussian space and the standard normal space. And the equation for that curve is the equation we saw here that we can use in arbitrary number of dimensions for arbitrary correlation between Gaussian random vectors. So that concludes what we wanted to see for the Gaussian. Now let's move to the log normal probability density function. So we're going to look at the univariate case, multivariate case, what are the special properties associated with it, and the Python code to use it. So we're going to say in the case of log normal that a random variable x is log normal if the log of x is itself normal. So if we look at the univariate log normal case, the key parameter to define its PDF are going to be the mean value in the variance in the log normal space, or for ln of x. So we can see that lambda is the mean of the Gaussian random variable in the log space, and zeta square is going to be the variance of the Gaussian random variable in the log space. So we can either say lambda or mean or mu of ln of x. We can either say zeta square or the variance of the ln of x space. Okay, we're going to untickle this in a moment. So keep in mind, mu x is the mean of x, my log normal random variable. Lambda is the mean of the log of x. So that's why we can write it as mu of ln of x. Sigma x square is the variance of my normal variable. Zeta square is the variance of the log of my log normal random variable. Okay, I know it can be confusing, and that's why we can write it as sigma square of ln of x. If we want to go between one space and the other, okay, we can do so using these two equations. So we can obtain lambda, or the mean of the log of x, as the log of mu x minus zeta squared divided by 2, where zeta squared is the standard deviation of ln of x, is the square root of the log of 1 plus delta x. Delta, which is the coefficient of variation of my variable. So remember, it's the sigma x divided by mu x, where for zeta approximately equal to my coefficient of variation, so sorry, the zeta is approximately be equal to my coefficient of variation if the coefficient of variation is less than 0.3. And typically this is something we're going to have in reliability analysis. We're going to be able to have this hypothesis satisfied. So you're going to end up with zeta parameters that are not too far from your coefficient of variation. So if we look at the PDF, so we're going to say that x, a log normal random variable, is distributed like a log normal PDF, parameterized by lambda and zeta. Okay, keep in mind, it's not zeta square, it's really zeta. And the PDF looks like this. We're going to come back to this in a moment. And this is defined only for the positive space. So we can see that if the mean of my log normal random variable is 2, the standard deviation is 1. The PDF looks like this. So the mean is 2, standard deviation is 1. And you can see that it's only defined for positive value. We see mu x, you see mu x minus sigma, mu x plus sigma. But this is defined from the parameter lambda and sigma, which represent, if we take this axis x, we take the log of x, it's going to be this space here. Okay, we just change the scale. And in that case, this is now a normal distribution. So basically, how is this defined? If we define a normal with mean 0.58 and standard deviation 0.47, it looks like this. I take the exponential of this space, it's going to give me that log normal random variable. Okay, we're going to dig a little deeper into this in a moment. So we're going to answer the question, how do we obtain that expression for the log normal random variable? Okay, we obtain it through the change of variable rules we saw in module 0. Okay, when we have function of random variables. So in this case, we're going to say that x is my log normal random variable defined for x, which is positive real numbers. Then x prime, which is equal to the transformation ln of x, is going to be defined in the real numbers. Okay, so if I take the log of something positive, it's going to give me something that is real. So I know f of x prime. I assume this is a Gaussian distribution that is going to be parameterized by lambda and variance, so for the mean, and zeta square for the variance. And I want to apply my change of variable rules. So I know from this that f of x prime dx prime must be equal to f of x dx. I know this is Gaussian. I'm looking for what is going to be the analytical expression for that PDF. So I'm going to send a dx on the left-hand side, and I must take it in absolute value. And now I need to find what is dx prime dx. So dx prime dx is simply going to be 1 over x. So now I can directly use the expression for f of x. That's going to be equal to dx prime dx, 1 over x, times the normal PDF, parameterized by lambda and zeta, evaluated for x prime equal ln of x. So if I develop this term knowing the expression for a normal PDF, I obtain this, which is the analytical expression for the log normal PDF. So we can use the Lognormal PDF in not only the univariate, but also the multivariate case because it's all derived from the Gaussian. So most of the property we're going to have for the Gaussian will be transposed into the Lognormal space as well. So we can say that if x1 to xn are jointly Lognormal, if the ln of x1 up to xn are jointly normal. So we can define again the multivariate log-normal space with respect to each of its marginal, defined by the lambda value, so the mean value for each of the marginal, and the zeta values, the standard deviation for each of the marginal taken in the log space. And when we want to define the joint distribution, we need to define correlation coefficient. And this correlation coefficient is defined in the log transform space. And here, keep in mind, there's not a one-to-one correspondence between the correlation coefficient in the log transform space and the one in the original space. We should obtain it from this distribution. So if we know the correlation coefficient in the original space, the log normal random variable, the correlation coefficient in the log transform space, the one that is jointly normal, is given by this expression, which is span on the coefficient of variation, the correlation coefficient, and the zeta values. And for again, coefficient of variation from our marginals that are smaller than 0.3, I'm going to have my log transform and my original correlation coefficient that are approximately equal. There's going to be only slight variation between the two. So if we want to look at the bivariate log normal PDF, it's going to look like this expression where you're going to see we're divided by 1 divided by sigma 1, 1 divided by sigma 2 here. This is the result from my the derivative between x prime and x that we saw in the derivation before. And it would look somehow like this. It's only defined in the positive domain for x1 and x2. You can see the marginal, you can see that joint PDF, and the same corresponding contour here. You can see the mean for each variables, and you can see the corresponding here lambda and zeta value. You can see correlation coefficient in the log normal space is 0.6, in the normal space is 0.62. So it's still close from each other. Now let's look at the properties of the log normal PDF. So first is going to be completely defined by its mean vector and covariance matrix, just like the Gaussian. We can say that the marginal distribution are still log normal, so that again allow us to marginalize without having to integrate. It inherits the property from the Gaussian. Conditional distribution are still log normal, again a property inherited from the Gaussian. And just like the Gaussian again, if we have no correlation, so my correlation coefficient equals 0, this implies the independence between my log normal random variables. For the Gaussian, we had the summation of Gaussian random variable was Gaussian. in the case of the log normal because there's an exponential transformation between the normal space and the log normal space. Now we're going to have the product of log normal Gaussian log normal variable is still log normal. So if I have x and y that are both log normal, x times y is still going to be log normal, and I can directly obtain the analytical expression for my hyperparameter by using the Gaussian rules, because since lambda and zeta I define in a normal space, I can directly sum these parameters because I have the transformation, a log transformation to go from x and y to the normal space. If I take the log of a product, it becomes a sum. I can simply sum my parameters just I had before. The central limit theorem still applies for the log normal. In the case of the Gaussian or the normal, it was the infinite sum of IID distribution would lead to a normal. In the case of the log normal, is the product of infinitely many IID distribution will lead to a log normal distribution. So if I have the infinitely many product of x1 to xn, they're all IID, the result is going to be a log normal distribution. So if we look at how to use the log normal in Python, we're going to use the same package as before, or we're going to use the SymPy here as additional package as well. So we want to define what is going to be from the mean value mx in the standard deviation of my log normal, say 1, 1. I want to define what's going to be my standard deviation for ln of x, the native parameter of my log normal, and its mean value, so mean of ln of x. So we always start by calculating the standard deviation because this one is necessary to compute the mean. So I define the expression we had earlier here, and we have the same thing for the mean value. Then I want to plot for x defined from -3 to 3. We can use lognorm.pdf or norm.pdf. And keep in mind here, this is a normal PDF, lognorm PDF evaluated for x and my two parameter, so mean and standard deviation in the log space. I can also manually create this PDF by saying I'm going to evaluate norm.pdf, the normal PDF, evaluated for the log of x with mean ln of x, and I divide by x. So these two are equivalent expression. We can, if we want, manipulate analytical expression, use the symbolic toolbox of, or the symbolic library of Python. So I'm going to define x under the underscore as my symbolic variable that I'm going to be able to manipulate into an analytical expression. So for my PDF, and then I can obtain my CDF by simply integrating analytically f of x with respect to x from 0 to x, my symbolic variables. So I can do algebraic manipulation with this. If I want to plot a multivariate CDF, in this case a two-dimensional one, the first thing I can do is that I can use a lambda function to define my transformation between my mean and standard deviation into SLN and MLN, my standard deviation and mean in the log transform space. These lambda functions allow me then to reuse these transformation functions without having to rewrite them again. They're kind of very short-end functions. And once I have transformed, so going from my mean value and standard deviation from my original space to my log transform space, I can reuse them into building my correlation coefficient in the log transform space using the equation we saw earlier. I build my mean vector in the log transform space, my covariance matrix in the log transform space, and then there's no dedicated function for a bivariate or a multivariate log normal distribution. You have to manually build it from the multivariate normal. So multivariate normal.pdf, we're going to evaluate this at the log of my tuple x1, x2 for mean of ln of x, covariance of ln of x, and I need to divide by the product of x1, x2, my tuple I want to evaluate. Okay. So this is how you would use a multivariate log normal PDF. Now we move to the gamma distribution. What is the gamma? How do we use it in Python? Gamma is defined for positive real numbers. So it looks like this. This is the expression for its PDF, where this is the gamma function evaluated for the parameter k. So the two parameters are k and theta. And if we want, this is the formulation for the CDF, where this is the incomplete gamma function, that little gamma here. And if we want to go from the mean and variance of my gamma random variable into its native parameter k and theta, we need to solve this system of two unknown two equations. And typically we're going to use the gamma distribution to model the sum of exponential random variable. And this is typically what we would get if we want to look at the accumulation of fatigue damage. So if we want to use the gamma in Python, we need to find a way to go from our mean value and standard deviation in the original space for the my gamma into those native k and theta parameter. So we can do this by using the symbolic library of Python in order to solve our two equation, two unknown system. So I'm going to define my two equations and I'm going to ask Python to solve it for me. So in that case, I'm going to be able to extract for my two values. Here, be careful, you need to convert these symbolic expression into a float number. So you need either a standard float 32 or a lower precision N16. So for k and theta. Okay, so this is how you would solve that system of two equation, two unknown, to get your k and theta from your mean and standard deviation. So once you have those native parameters, you can say, okay, I want to plot x over this range, and I want to evaluate gamma rd.pdf. Let's say again is input k and theta, the two parameters we found there. If you want, you can do some symbolic manipulation as well, or algebraic expression manipulation using the symbolic library of Python. Now we're moving on to the Gumbel distribution. What is it? How to use it in Python? So the Gumbel distribution takes as parameter mu and beta. So the mu again is not the mean. It's the specific to the Gumbel distribution, which is defined in the real space. So this is the expression for the PDF of the Gumbel, the CDF of the Gumbel. And if we want the relation to go from mean and variance of my Gumbel to the native parameter mu and beta, we need again to solve the system of two equation, two unknown, where gamma is my Euler constant equal to this quantity. And in practice, we use the Gumbel distribution to model the maximal value obtained over a fixed interval. So for instance, what is going to be the highest traffic load on my bridge, or what's going to be the highest water level in my lake or my river on a given amount of time. So if we want to use it, again, we need to rely on the symbolic library to obtain or system of two equation, two unknown that we're going to solve to extract my parameter mu and my parameter beta. And then I can use here my Gina extreme because the Gumbel is a special case of the generalized extreme value distribution, GEV. So I want a PDF with parameters 0, beta, and mu. If you use other values here, is going to be the other special case of the GEV distribution. And you can again manipulate some analytical or algebraic formulation using the symbolic distribution, the symbolic library. The last distribution we're going to see is the beta distribution. So what is the beta? We're going to say X is distributed like a beta distribution for parameter alpha and beta. So this has the particularity that it's only defined on the interval 0 to 1. Okay, instead of being positive, real positive or real numbers, it's just for a fixed interval. And its PDF looks like this. It's going to be x power alpha minus 1 times 1 minus x beta minus 1 divided by b of alpha and beta, where that b is that beta function, which simply represent a normalization constant for that numerator that we have here. And a special property about that beta, it's there very useful to model the uncertainty we can have about probability. Okay, let's imagine a sampling space where we have two possibilities, either an event A or its complement. So what we can do is that we can model the probability of the event A as a beta random variable X. Okay, because we don't know yet what is the probability of the event A. We want to model the uncertainty we can have about a probability. And to do this, we would use a beta. And we can say that the probability of the complement of A, if probability of A is X, is simply going to be 1 minus X. And this is what we would typically use the beta for. And there's a really nice property that the two parameters alpha and beta are interpretable. What does it mean? The alpha you get would be the number of observation of the event A you get. And beta is the number of observation of the complement of A. So when you want to characterize a probability, according to the number of realization of the event A, you see that the beta PDF with parameter alpha and beta will tell you how much knowledge you have about the probability of that event A. So this is an example of representation of the beta PDF. If alpha equals beta equal 1, you have a uniform PDF in the range 0 to 1. If alpha and beta equals 3, it looks like this. If beta equals 0.5, alpha equals 3, it looks like this. And let's put this into application. Let's imagine that you want to flip a coin. You know when you flip a coin, the probability of occurrence of head or tail is 50-50. What if you have a thumbtack, like these represented here, or the one I have here in my hand? So what is the probability of landing on head and landing on tail? So I can have a prior knowledge, but I don't know yet exactly what is the probability of each. But how can I characterize this? I can use the beta distribution to do so. So my sampling space is going to be head or tail. And I'm going to say that the probability of landing on head is X, what I'm going to characterize as my beta PDF. So if I do some throws of my thumbtack and I count the number of times it lands on head rather than landing on tail, I'm going to be able to characterize my knowledge of what should be the probability of landing on head. So alpha is going to be the number of landing on head, and beta, my probability of, or not my frequency, not my frequency, the number of time I've landed on tail. So if we look at this in practice, it's going to look like this. So I prepare a little code that gives me right now I have n equals 0 throw. I have not done any trial yet. So for now, I assume that I'm going to have a uniform prior knowledge for whether it's going to be what is going to be the probability of landing on head or tail. And as I'm going to do some throws, like let's do a first throw, it landed on tail. This is how this knowledge changes. And you see that the pink region that is here is represent the 95% coverage region is reported here as a function of the number of observation. Do a second one. Now it's going to be add. So I change my knowledge. I'm going to do another one. It's going to be add. It's going to be add. 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 So you see how my knowledge is changing as I'm obtaining realization of an event. And this is what we can model with the beta PDF by simply counting the number of realization that automatically update my knowledge of a physical phenomena I want to characterize. Okay, extremely powerful. We're going to come back to this in chapter 10. So this is for my beta PDF. If I want to use it, so I'm going to define my parameter alpha and beta that I represent here as A and B. I define which range in which I want to plot. So I'm going to define here my beta PDF, A and B. And I'm simply going to plot it here. There's nothing special with it. We also have, if we want some explicit formulation to obtain A and B from the mean and variance of it. So if we do a summary of what we covered here for the univariate normal distribution, it's defined in the real space, parameter, the mean, and standard deviation. Keep in mind that we always represent the parameter as the variance, but whenever we use in Python to define, they're going to use as parameter sigma, not sigma square. So be careful not to be tricked there. So if we want to sum Gaussian random variable, we're going to sum the expected value. We're going to sum the terms on the covariance. And the result from the sum or linear function or affine function of Gaussian random variable is still Gaussian. This is a very key property we're going to reuse in the next module. So we can have the distribution for multivariate case, define by mean vector and covariance matrices. We have access to conditional distribution that are still Gaussian. And we can do transformation from arbitrarily X space to the standard normal space. And this is what we're going to reuse to define the reliability index that we're going to see in module 2. For the log-normal distribution, is defined in the positive real domain. We can have closed form solution for the product of Gaussian. So if product of log normal. So if x and y are log normal, their product is still going to be log normal. We have the gamma defined for positive real number. We have Gumbel for real numbers, and we have beta for interval 0, 1 that is typically used to model probability. So in practice, how can we use these PDF to model real quantities? To this, you should refer to that GCSS, the Joint Probabilistic Model Code, the Joint Committee for Structural Safety. You can see here that probabilistic code divided in 3 parts. So part 1 is going to be a general basis for designs of structures, where part 2 you have all the specificities with respect to the loading model. Part 3, all the specificities for resistance model. So how each of the quantity involved in your design or your analysis of a structure should be modeled by which type of variable, which type of uncertainty. So if we take a simple one, for instance, structural steel, we can see that we have 5 parameters that could be used to characterize steel: the yield strength, the ultimate tensile strength, the Young's modulus, Poisson ratio, and ultimate strength. And we can see here they recommend ways to model it. For instance, we should model these 5 parameters using multivariate log normal distribution. And what parameter should we use? They recommend that for expected value, we should use the nominal values specified in codes or in drawing. For the standard deviation, we obtain them from the coefficient of variation assuming these values. And they provide a correlation matrix between those 5 parameter to be used. If you have different knowledge, you can use different one, but these can serve as a starting point. And you have in that probabilistic code values for all types of common things you're going to be using for analyzing either building structures or dam or bridges for both the loading and for the resistance model. And in addition, you also have example of application of reliability studies on some applied cases. So now the last thing we want to say before closing out this chapter is imagine that we want to plot for a same parameter mu x or mean equal 3 and standard deviation equal 1. These PDF for the 4 distribution we saw: normal, the log normal, the gamma, and the Gumbel. So if I ask you, can you tell me which one is which? So we might say the only one that is symmetric is the Gaussian. So probably in purple we can say this is Gaussian. But what about the other? We cannot really say which one is which. So if we can tell visually which one is which, why does it matter which distribution we choose? Actually, it matters a lot. Why? Because if we look at the tail of the distribution, and this is where reliability analysis are, because we're looking at rare events. So in the order of 10 to the minus 4, 10 to the minus 6, 10 to the minus 7. So these are rare events occurring in the tail of distribution. And if we zoom in, we're going to see that the tail are drastically different for the probability distribution we choose. And look at the normal. This is the one that has the lowest content in the tail. If we go further out in the tail, we see that the discrepancy is even further expanded. So it is super important to correctly select the probability distribution for the phenomena you want to model, because there's going to be a very wide discrepancy in the tail, and this is what you want to model correctly. So if you have questions about how do I choose my distribution, refer to the GCSS probabilistic code in order to get you started into what type of distribution and what parameter to use for what you want to model in practice. So that closed that module 1 we saw about probability distribution. Now we can tackle the next module, that how can we formulate reliability problem. This is going to be the key places where we're going to define what is the reliability index, how is it related to the probability of failure.